We will talk now about avoiding sending sequences. So far, messages contain entire sequences, but sequences can be very large. For example, if a replicated state machine is used to maintain a transaction log in a database, then the log could be easily exceed gigabytes. Therefore, the algorithm is not yet practical. With the next optimization, we were going to eliminate sending redundant subsequences. We focused first on promise messages. So let us see now where we send sequences unnecessary. When acceptor gets a prepare message, it sends a promise with an entire sequence here. Also, after you complete the promise, you are going to send a sequence to all acceptors while you are still in the prepare phase, and then incrementally you are going to send sequences again to all acceptors in the accept phase of the leader, and also here we have sequences that are going to be sent when you decide. So we want to eliminate all of these, and we are going to focus now on this one. Just to outline the idea of the whole section on avoiding sending sequences. So a prepare needs to include the length of the decided sequence that the proposer, which is the leader, knows. Promises need to send back to the proposer the difference between what it knows and the decided sequence of the proposer. An accept needs to carry only the deltas between the new extended sequence and what each acceptor knows. And accepted need to carry the length of what it has accepted, and a decide need to carry only the extension of what is already decided. So let us look to the idea of trimming the promise. So a leader L sends a prepare message to a replica P, and that replica P responds with a promise message. So the leader sends here a message, it arrives to a replica, and the replica sends back a promise to the leader. The promise message contains entire sequence, so it contains the accepted sequence at P. L knows that the sequence that will eventually be adopted by all replicas is an extension of the decided sequence at the leader. So here is a change to do it. So the prepare message, this message, should include the length of the decided sequence at the leader and the highest round number where he accepted some elements in the sequence. Now a promise message, it will include the round number of the accepted sequence at the replica and the suffix of its accepted sequence, and this suffix is indexed by the decided sequence that it got from the leader. And that is only true if the round where it accepted some value is actually higher or equal the round number where the leader accepted some value. This means that the replica, or the process P, which is the acceptor and learner, the replica is actually knows more information than what the leader knows. In the other case, where the round number of the accepted sequence at the replica is less than the round number of the accepted sequence at the leader, then it does not need to send any information. So it will send just an empty suffix, and it will send, of course, its round number where last accepted something. It should be clear that why is that? Because if you remember how we adopt a sequence, we adopt a sequence that have highest round number and longest sequence. And in this case, the replica's round number is lower, so the sequence is not interesting and it will never be adopted. This gave us the following, is that the proposer can reconstruct the adopted sequence, okay, by collecting a majority and using the max function to collect which one is the highest round number and highest sequence. This should be clear. So let us look to this now by a number of examples. And we illustrate it by the ballot array. Okay, fine. So now we have P1 becoming a leader, so he is here at round 3. So his decided sequence is this sequence C1, and this has been decided in round 1, and he has a suffix which is A, B, and D. So now P1 consults a majority. It will consult itself and either P2 or P3. And how it does that, as I said, by sending the length of its decided sequence, and that length is 1. Okay, so in this case, P2 will send the suffix. So if you look to P2, the suffix of that length, which is 1, so it will send this information, and P3 will send the suffix, which is this information. P2 will say that the highest round where I accepted any values, it is round 2, and the suffix of the decided sequence is that, C2, C3. And P3 will say something similar. The highest round number for me is 2, and my suffix is the sequence C2. So now if P2 is consulted, because I can either consult P2 or P3, so what happens now if I consult P2? I got this sequence, and I have my own sequence, and then I will adopt, of course, my sequence now will be the previously decided value, and this will be the longest adopted sequence at this point after C1. So I have a sequence C1, C2, and C3. And so that's what we get here. And then, of course, if I have accumulated some local commands, so I can add them to the sequence. So after this ends, we have that sequence, C1, C2, C3, E, F, and G. Just a note, as you can see, when P1 was elected a leader, it is lagging behind. Its round was N1, and this leads to transmitting long sequences from the other replicas to be able to synchronize. And if we follow the same argument again for P1, a decided sequence, so P1 is still the leader, the decided sequence is C1, and now we are using P3. So in this case, if P3 is consulted, this sequence is added to C1, and it will be then locally extended by E, F, G, and we get now the sequence at the leader. C1, it's already decided, C2 decided in a sense in round 2, and E, F, G. So you can see when you do a leader change, you can get different sequences to start with, but everything decided is a prefix of that sequence. So let's take some other example where another process is a leader. In this case, we choose P3 as a leader. So P3 has this decided sequence, C1, C2, and its own highest accepted round number is 2, and there is nothing else. The suffix is empty. And now again, P3 either consults P1 or P2. If it consults P1, and that is an interesting note, if it consults P1 will just send no information. It will send an empty sequence because its round number is actually lower than the leader's round number. So here a case where we didn't send any information from the replicas to the leader. But on the other hand, if it consults P2, then P2 will send as suffix this value C3. Remember that at this point and at this point, the chosen sequence is C1, C2. So it doesn't need to take C3. And these are the ones that is possibly have been decided at this stage. Okay. So if that happens and we pick P1, so what's going to happen then? That the leader, which is P3, is going to extend its own sequence by just the local commands it has been saving during the prepare phase. And that will be the output. I think this makes things clear. On the other hand, which is very similar reasoning, if P3 chooses P2, so this sequence will run. C2 is going to send to the leader, which is P2, only this part. And the leader then, he is going to choose the sequence C1, C2, and C3. That's it. And then extended it by his local commands. If P2 is a leader, we are going to have similar behavior. Actually, the interesting thing about P2 is that P2 has the longest sequence and the highest round number, and therefore actually he will not get any sequences either by choosing P1 or P3. So in a sense, P2 might be the most efficient leader, but this we cannot control. Whatever happens here, there is nothing that the other replicas can give to him. So this is the algorithm. So let us see what are the changes we had to do for this. The first thing now, the set S will include suffix of sequences that starting after the length of decided sequence. And here is a suffix that's coming from the leader himself. In the prepare phase, he has to send to all replicas except himself the length of the decided sequence and the round number that he last accepted anything in. When a replica gets the length of the decided sequence and gets this n, as we said, then if the accepted sequence at the replica is greater or equal n, then it has to send its suffix. Otherwise, it sends the empty sequence as before. And that will be sent back to the leader. Let us now look what happens when we collect a majority of suffixes. So we use again the max function on that majority. And here is the max function. We have seen it before. I'll just put it here again. Take the sequence with the highest number and the one that is longest. We've did that before. And what we do then, we basically take the decided sequence, we append the suffix, and we append new command that has been accumulated during the prepare phase. And then we send these commands to all acceptors. This again is going to be optimized later. But this is we have seen. So that's not new. Okay, we are in a very nice position now. What is left actually is to optimize the accept messages, the decide message. These are the messages that we have to optimize. And in fact, the first accept message is an important message, and we actually are going to change its name. After the first accept message is accepted by all acceptors, then the replicas are actually in complete sync with the leader. So the leader has only to augment these replicas with new commands. This is the basic idea. So let us see it in the next unit.